Students, today we will solve problems based on diodes. This is going to be first tutorial on analog electronics part of course EE101. So here we will take up various problems related with diodes and try to solve them. So first problem that we will take up is this circuit. Here we can see that we have a diode here. So here we have a diode, and this is being used to charge this 12-volt battery. And we have a source here, and this source is sinusoidal with amplitude 24 volts. So we have to find out what is the fraction of this complete cycle of the input for which this diode conducts. That means this diode is on. So fraction of each cycle during which diode conducts, that means diode is on. And then of course we'll have to also find out what is the maximum value of diode current, this ID max, and what is the maximum reverse bias VD. This so these are the three things we have to find out. So try to find out these three things.
Hello, sir.
Yes.
Yes, sir. The fraction is 1 by 3. Is it correct?
Fraction is 1 by
1 by
3.
3. Peak
Yes.
value is 0.12 ampere
Yes.
and maximum reverse bias voltage is 36 volt.
Yes. Okay, so let us see that how to solve this one. So here, this Vs is sinusoid with amplitude equal to 24. So in the first half, this in will become positive and this in is negative. So diode will experience a forward bias voltage in this direction, in the direction of the diode. So diode will turn on, provided the voltage difference between node A and B is positive. So in the other end of the source and plus 12, they are connected here. So this VAB is Vs minus 12. So VAB should be greater equal to 0. that means Vs should be greater than 12. Only in that case, there will be forward biasing and that will turn on. So this, we have to draw a line at 12 volt. So our diode will turn on at this moment and it will remain turned on for this portion. So actually we need to find out this theta. What is this theta? If we know this theta, we can find out duration for which it will be turned on. So in this case, we are taking our Vs as 24 sine theta, and this should be equal to 12. That means sine theta should be equal to 1 by 2. So this implies theta should be 30 degree. So this is 30 degree, right? And then this portion starting from here in this direction, this will also be 30 degree. That means this duration over which it is on is 30 degree. So that will be on. Thirty degree out of 90 degree for the, no, sorry, there's a mistake here.
So that will be 120 degree.
Yes, you're right. So this is 30 and so this will also be 30. So this is going to be actually 60 degree, right? So this entire 1/2 cycle is, so diode is on for 30 plus 30. Diode is actually off for the first 30 degree portion, this portion. This is a
Sir,
half duration. Similarly, this is also half duration. So this will also be 30 degree. So remaining portion is 60 degree. Oh, no.
sir,
This is
120 degree.
120. Yes, you're right. So so this whole half is 180 degree. So 180 degree minus 60 is 120 degree. Sorry. So that is actually off for 30 plus 30 out of 180 degree for the first half. Similarly, for the second half also, it will be on. No, it will be actually on only for this portion, 120 degree. So on for 120 degree. So therefore, fraction is going to be 120 divided by 360 is equal to 1 by 3. So for T by 3 duration, it will be on. Now, when it is on, we have to find out what is the maximum current that flows through diode, ID. So during the on portion, this is going to be the voltage. So when it achieves this maximum voltage, this Vs becomes maximum voltage. In that case, this diode and resistor, they will experience the maximum voltage. And when diode is on, it can be substituted by short circuit. So when diode is on, this is going to be the circuit, and this is 12 volt. This is 24 sine theta. So we see that the maximum voltage that resistor R will experience is VR is 24 minus 12 is equal to 12, and this is going to be R into I. So the maximum current, the same current flows through diode also. So this is going to be 12 divided by R. So this is 12 divided by 100, right? So this is 0.12 ampere or 120 milliampere. So this is the maximum diode current. Now we have to find out what is the maximum reverse bias that diode will experience. So diode will experience reverse bias uh, in this portion and in this portion. So we see that the minimum negative voltage that this node will experience is this moment, and this is going to be minus 24 volt. And the node B is already connected to 12 volt, and this will be connected to minus 24 volt. So the maximum reverse bias voltage bias is going to be minus 24 equal to minus 36. So we will have to suitably choose a diode which can tolerate this much of reverse bias, because we know that if diode is exposed to a large reverse bias, it will usually break down and it will again start conducting. So diode does not remain off under all reverse bias voltage condition. There is a limit beyond which it will again start conducting. So here we have a resistor RL connected across a Zener diode, and it is said that Zener breakdown voltage is equal to 20 volt, and the maximum, this IZ max that it can experience before it burns out because of the excessive heat, is equal to 60 milliampere. And this one is 200 ohm, this RL is 1 kilo ohm. Then it says that what is this range of VI? There will be lower limit and there will be higher value of the input voltage, such that this Zener diode is on. That means this IZ is greater than 0. So try to find out this lower value and the higher value for the input voltage, so that Zener diode conducts in reverse bias, of course. So this polarity will ensure that Zener always experiences a reverse bias. So we just need to focus on the voltage of this VI.
So
Hmm.
VI will be from 24 to 36 volt.
Yes. So this is what we have been given. So here we know that when this VI is increased, there will be current I, which in general will increase. And in general, this current will get splitted into two branches, that is IL and I Zener. So we will always have I is equal to IZ plus IL in general, whenever IZ exists. But we know that for IZ to exist, VZ should be equal to 20 volts. So that means as long as this voltage is not 20 volt, Zener diode will not conduct, and in that case entire current will flow through load. It is this path that entire current will take. So this is what is going to happen when Vi is low. Okay. So for low Vi, say for example, when Vi is just 1 volt, in that case Vz in no way can become 20 volts. So Vz, this Zener diode is going to be off in that case, right? So for low Vi, Zener is off. This implies Iz is equal to 0, and in that case, therefore the circuit is, under such situation we are going to have this circuit. Zener is off, so there is a broken path there, and then we have our remaining components. Right. So here we can see that when this Vi increases, the current is going to increase, and this VRL, this voltage is also going to increase. And keep in mind that this voltage VRL is ultimately going to be the voltage that Zener will experience, right? Which is kept here, but currently it is off, right? So when this Vi increases, this VRL increases, and the voltage across Zener also increases. So there is a lower limit beyond which VRL will become equal to VZ, and in that case Zener will switch on, and then there will be IZ current also. Before that IZ is going to be 0. Currently it is 0. So we have to find out what is VRL, and this VRL is RL divided by RL plus R1 into Vi, and when this one is greater is equal to VZ, diode will start conducting. So the lower limit on this Vi you can see is when this equality is taken. So Vi minimum, which is VL, we will call, is going to be VZ RL plus R1 divided by RL. So this will be 20 into RL is 1K, R1 is 200 divided by RL, which is 1K. So this becomes 20 into 1200 divided by 1000. So this will turn out to be 24 volt. So when Vi is greater than this 12 volt, diode will start conducting. So lower limit on the input voltage is decided by condition that diode should start conduct. Now there is an upper limit on this Vi. So this upper limit on Vi is decided by the fact that diode should not experience a voltage more than, so what is given to us is Iz max is equal to 60 milliampere. So this parameter will dictate the upper value of this Vi. So high will be decided by Iz max. So now let us see that how this IZ max is going to be decided. So we have seen that whatever current is provided, this will get splitted into Zener branch and the load branch, IZ and IL. So I is equal to IZ plus IL. So as this input voltage increases, this current increases, and there will be tendency for these two currents also to increase in general. When this increases, there is possibility of increase of these two. But here what happens is that when Zener is on, it will be behaving like a voltage source of value 20 volt. So the circuit is going to be like this. Where Zener switches on, this is the circuit that will be operating. And this is VI. VI is greater than 24 volt. Right. So then VI increases, I increases. So this IL cannot increase. This cannot increase. So only increment that will happen in current through Zener. Right. So IL gets fixed. IL is constant once Zener is on, and that is going to be 20 volt divided by 1000. That means 20 milliampere. So load will always get this much of current as long as VI is greater than 24 volt. So we have to see that the maximum of this will be decided by IZ max, because IL is always fixed. And this is 20, we have already calculated milliampere, and this is given maximum is 60 milliampere. So the total maximum current that can be supplied by VI before diode gets burned out because of excessive heat developed is 80 milliampere. Right. So now we know the maximum current through R1 is 80 milliampere. And this end, the other end is always at 20 volt because of the Zener. And this end voltage is at VI. So now we have to find out VI minus 20 is going to be I max into R1. So here you can see that for this I max, VI max will occur. Right? Actually, this equation is general. It will always be valid under this condition also, as long as Zener is conducting. So we now, to find out the maximum of this, we have to find out maximum of this current. So VI max is equal to R1 I max plus 20. So R1 is 200. I max just now we calculated. So this is the, this is the upper limit on the input voltage, VH. So VI should be between 24 volt and 36 volt. In the next semester, there will be a lab component based on the all the electronic portion that you are studying, both digital and analog. So in one of the experiments that is called voltage regulator or regulated supply, so you will encounter this circuit. So there will be a Zener circuit, Zener diode, and the load will be connected across it, and it will be fed basically by rectifier. So there also we need to carry out these kinds of calculation to find out the what should be the current rating or voltage rating of the Zener. So now we are going to solve this question number 5. So there are circuits given in figure 4, and we have to find out the output waveform, and the input waveform is given in 4a. So this is the input waveform to each of these following circuits, and in this circuit we have to find out what will be the output waveform. So first let us try to solve this one. So what will be this output? Input is already given here. So we have been given input voltage of sinusoidal form with amplitude Vm, and we have to find out what is Vo. So in all the circuits involving diode, we have to find out whether diode is on or off. So that means whether diode is forward bias or reverse bias. So whenever we have a voltage across diode in the direction of arrow, suppose voltage is such that this is the direction of voltage. That means this one is at higher potential, this is at lower. Or you can say that if electric field, if you try to look from the electric field point of view, then the direction of electric field is like this. So if the direction of voltage or electric field matches with the direction of diode, then ideal diode will be on. And we will substitute the diode by this closed switch. And whenever diode is what is called reverse bias, that means diode is in this direction, but voltage uh, slope or the electric field direction is like this, then we say that it is reverse bias. In that case, diode will be substituted by open switch, or it could be like this also, and we say that this is off. So we just try to find out whether diode is forward bias or reverse bias, substitute by this model, and then use the usual knowledge of solving the circuit, right? So now here we see that uh, during the first half, this is positive, this is negative. So here you can see that this negative voltage will uh, be available even at the base, at the anode of the diode also. And in this case, diode will experience, voltage or electric field in this direction, which is to the opposite of the its direction, this direction. So that means during first half, diode is going to be off. So for the first half, the equivalent circuit is going to be like this. here. So we see that output port was already open, and diode is open circuit. So there can be no current through this resistor, and that is why this current, whatever may be the direction, is going to be 0. So that is why this I is equal to 0. So this VO is going to be 0. So this is the situation during the first half. Now during the second half, of the input, what will happen is polarity of the input will get modified. It will become like this. So now in this case, we can see that this positive voltage, its effect will be available at the anode, and in this case, there will be voltage or electric field with this orientation. So this orientation is similar to the orientation of the diode. So diode is going to be on in this case. So during second half, the equivalent circuit of the diode is going to be that of a closed switch. And then here we have our input, right? So output is actually measured in this way. That means this is going to be the reference node, and the node of the voltage of the upper node is going to be measured and pointed out. So in this case, we can see that output is going to be the second half of the input itself. So VO is going to be minus VI. So we have already seen that if this is the input, then we just now calculated output is going to be 0 for the first half, and then it is going to be input during the second half. So this is basically half wave rectifier, which blocks the positive half but allows the negative half. Right. So now we are going to take up a different circuit. Say, for example, this one, last one. So in this case, what is going to be output?
To be in second half.
When you are going to get output?
In second half.
No, output will exist only in the first half.
Sir, it will be when Vi is greater than V, like in some part of first half.
Yes. So let us try to see that what is the solution for this case. So this is what always keep in mind. This is what you should try to do. Try to align the voltage direction with the direction of the diode, and then try to conclude whether diode is going to be turned on or it will remain off. Right. So this is part E. Okay, so we have this circuit. We have a voltage source V, and then we have our diode, and then we have resistor, and output we are taking across VO, and this is VI, right? So now here we can see that there are two sources. One is VI, which is going to vary sinusoidally with amplitude Vm, and second is this constant voltage of voltage V, right? So I am showing it using only a pair of line, but actually this is a battery, so there will be two such symbols. Okay, so we have to find out when diode is going to be on. So let us see the scenario during first half. So during first half, what we have is, we have voltage due to this voltage source. This will always be in this direction of strength V. right? And this is going to be constant. While this Vi is going to establish uh, another voltage, which during the first half is going to be in this direction. And this is varying. So this will be increasing, in fact, during the first half. So it increases from 0, becomes Vm, and then decreases, right? So the net voltage that diode will experience will be decided by the simple addition of these two, vector sum of these two, right? And only when the net is in this direction, diode will turn on, right? So here we can see that V is constant, but Vi is increasing. So definitely in the beginning, net voltage is going to be in the reverse direction, in the direction of constant V, right? So during the uh, positive half, during the positive half of this diode is definitely going to be off. So only when this this input has increased and it has become equal to V, then there will be net voltage in the direction of diode and diode will turn on, right? So only when this input is above this threshold, which is V, then only for this portion, what we will have is V minus V greater than 0, implying diode is on, right? And so now let us see that what happens when diode is on. So this is the duration when diode is going to be on, and for the rest of the portion diode is going to be off. So when diode is on, this implies diode can be replaced by short circuit like this, and then we have our Vi here, and then we have here resistor, and then output voltage, right? So now you can see that Vo is going to be Vi minus this constant voltage V, and this will be valid only over this portion, right? So what we are going to get, if this is our input and this is V level, then my output is going to be non-zero only over this portion, and it is definitely going to be 0 for the rest of the portion of the cycle. So output is so this is going to be my output, and this maximum is going to be Vm minus V, right? And this cycle will repeat. So in all such circuit, most important thing to do is this portion, this thing. You have to find out all the voltages across the diode and find out the net voltage, and then you can easily decide what will be the output. Now let us take last question. So here we have again a diode circuit, but now this time we have capacitors also in addition to the usual resistor, and now it is being excited by a square wave between V and minus V. So here objective is to find out VO. Again, ideal diode. So this is one thing you have to keep in mind. Second is that this time period is quite small compared with the time constant. So time period is significantly small. That means uh, there will be hardly any opportunity for capacitor to get discharged if RC circuit gets formed, which we will see actually invariably gets formed also. Okay, so here also we will have to find out what happens to diode during each half of the input. And as I pointed out, we basically need to find out what is the status of the voltage across it, in which direction it is, and in which direction it is actually basically because we are considering ideal diode. So here we see that in the beginning, assuming that there is no charge on the capacitor, and so what we have is only positive voltage equal to V. So this is the first half scenario. So here we see that there is a voltage which will establish electric field like this, or voltage distribution along the circuit is going to be in this direction. So here we see that voltage and diode both are aligned in same direction. So during first half implies diode is on. So when diode is on, we can redraw the circuit with diode substituted by short circuit in this way. Here. So we see that this resistor across which we are measuring this output voltage is basically short circuited. That means both the ends are connected by a conductor. That means both will be at the same potential. That means VO is going to be 0. So during first half, this is what will happen. First thing that will happen is VO is going to be 0. This is first thing that will happen. Second thing that will happen here, you can see is that the negative terminal of the input is now connected to the other end of the capacitor. So what happens? This VI gets connected across the capacitor. And so since there is no resistance involved, so this VI is directly getting connected here between the two nodes. So this capacitor will get very quickly charged, definitely during the time period T by 2. That means over this period, which is T by 2, the capacitor will get charged to a voltage V. So during the second half, what we are going to see is that there will be capacitor with voltage plus V in this orientation across it. And then we have here resistor, and then we have here diode. So during second half, this is what is going to happen. So now during second half, the polarity of the input Vi gets changed and it becomes like this. So Vi is V, but now polarity is in this way. So when you flip the polarity, you can remove the minus sign that will be usually present here. So that is why I'm not showing this minus sign here. Right? So now you can see that we have two voltage sources now present in the circuit. Right? So because of this Vi, you can see that there will be electric field in this way. Right? And because of C, there is going to be again electric field in the same direction. So now here you can see that diode experiences two fields, both are in the opposite direction to that of the diode orientation. So this implies diode is going to be off. So we can now substitute diode by open circuit. So equivalent circuit is going to be like this now. So here we already have V, and here again, because of the negative cycle or the second cycle of the input, we have Vi. So now you can see that this VO, so node A is connected to the negative terminal of the capacitor. Node B is connected to the now positive terminal of the input, and both are V. So what VO is going to be now is magnitude wise 2V, this V plus this V, right? So this is going to be, but we are measuring opposite polarity. This one is positive, but for measurement we are taking this as negative. So this is going to be minus 2V during the second half. So now if we have this input waveform plus V to minus V, this is Vi, then what we are going to get for the output is something like this. It is going to be 0 for the first half, and then minus 2V for the second half. So this is going to be VO. Right. So what this circuit has done is basically it has shifted the DC level present in the input. Right. So it has added minus V to this input. So VO is Vi minus V. So this is a DC level setter. So similarly, you can analyze the other circuit. So once again, most important aspect is doing this thing. That means drawing all the electric field around the diode, and then concluding whether the diode is on or off. And once you know the on and off status, you can substitute them by their equivalent model and then analyze the circuit. So similarly, other circuits can also be analyzed. So now we have additional voltage sources here. So in general, there will be three sources: one voltage across capacitor, the input, of course, and this V1. So we have to find out the cumulative effect of all these across the diode.